Alright, welcome to my channel. Today we'll be looking at an example of a Sturm-Liouville problem. Now, this is the question: find the eigenvalues and the corresponding eigenvector of this Sturm-Liouville problem. So we are provided with these boundary conditions. So to solve this problem, you have to know that we need a non-trivial solution for this Sturm-Liouville problem. And how does a trivial solution look like? If y is 0, the easiest solution you can give to this problem is to say that y is equal to 0. And if y is equal to 0, the second derivative at 0 of y will obviously be 0. Then if you insert 0 into this problem, you just get 0. That is a trivial solution. So what we are looking for is a non-trivial solution. That is, y won't be 0, but then if you insert that value you get for y into this problem, it still gives you 0. That is a non-trivial solution. But this non-trivial solution actually depends on the value of the lambda. So that is why we are going to consider the possible values of lambda and see where we have a non-trivial solution. So first of all, let's look at the first case. We call it the case 1. So at this case, the lambda is 0. So if you put 0 into your problem, you get d2y ds squared plus 0, and everything there becomes 0, so you get equals to 0. Then to solve for y, you integrate. So if you integrate with respect to x, if you integrate this with respect to x, you get dy dx is equal to c. This is 0, so if you integrate 0, you get a constant. Then if you integrate again dy dx with respect to x again, if you integrate this, you get if you integrate that, you get if you integrate this, you get y is equals to cx plus, let's say, k. So these are solutions. So let's see what will be the value of y with those boundary conditions. So if you check, we are provided with the first boundary condition, which is y of 0 equals 0. So this means the value of x is 0. At the point where x is 0, y is 0. So you can say that at s equals 0, y is 0. So if you insert that here, it implies that your k is 0. So let's use the other one. So we have at s equals pi over 2, your y is 0. So if you insert that, you get c times pi over 2 plus 0. Your k is 0. So this also implies that c is 0. So now that we have c to be 0 and we have k to be 0, then if you insert it into the answer we get, the general solution that we get, you will get y is equal to 0, and this is a trivial solution. So remember, I said we are looking for a non-trivial solution. So let's go to case 2. So let's look at the second case, case 2. So case 2, lambda is less than 0. So it is better you define lambda in terms of something that have a squared. So let us set lambda to be equals to minus m squared. So this is also a negative number because m squared is a positive. This one is greater than 0. You get, it's positive. So if I should negate it, like use minus to times it, this one will be less than 0. So we can have our lambda to be this. So there's a reason why we choose lambda to be minus m squared. It helps us when we are solving the second order equation. So coming back to the second order equation, we have d2y ds squared plus lambda y equals to 0. So if you insert the value, okay, let's use k minus k squared. So if you insert the value of lambda there, you get minus k squared y is equal to 0. So this is same thing as 2ds squared minus k squared y, which is equal to 0. Now, solving a second order differential equation, so this becomes m squared, the characteristic equation becomes m squared minus k squared equals to 0. If you take k squared to the other side, you get k squared, then square root of that, which will give you plus and minus k. So that is what we get for m. So this is distinct roots, like we have m1 to be k and we have m2 to be minus k. So in previous classes in 241, when you have a distinct root, your solution will be a exponential m1 of x plus b exponential m2 of x. So now our m1 is k, and then our m2 is minus kx. So this is our solution. This is known as the general solution. So after having this general solution, we need the unique solution, that is when we use the boundary condition. So at s equals 0, y is equal to 0. So if you put 0 for y and you put your a, then s is 0, so you get 0 here, plus b exponential 0. So this will give you a plus b. So which means a is equal to minus b. If you make a the separator formula, so you can just keep this, call it equation 1, just call it 1. So let's use the other one. At s equals pi over 2, y is also 0. Okay, so at this point, you substitute it into the general solution, you get 0 is equal to a exponential kx plus, okay, exponential pi over 2, because our x is pi over 2, then b exponential minus k pi over 2. But we've already said our a is equal to a minus 2, a is equal to minus b, so you put minus b here, then k pi over 2 plus b exponential minus k pi over 2. So at this point, if you bring out b, you get minus k pi over 2 plus minus k pi over 2. So okay, what can we do here? Okay, this can also be written as 1, this, because of this minus, according to law of indices, we have s squared minus 1 is 1 over x. So that is k pi over 2 is equal to 0. Okay, there's 0 at the back, there's no need for this, equals to 0. So you have 0 beta. Okay, so you have e k pi over 2. So that is LCM. Then you get minus ek pi over 2, because this one is over 1. So if this divide this, you get this back. So if you times that, you get the twice over of it, which should be k pi over 2 also. Then if this divide this, you get 1, so that is plus 1. So this will give you b into brackets. You can apply law of indices here, so that will give you k pi, because you have pi over 2, k pi over 2 plus k pi over 2. Adding it up, you get 2k over 2, that is k pi, when 2 cancel 2. So this is plus 1 over e k pi over 2. What can we do here? So at this point now, we have 0 is equal to b plus 1, then divided by ek pi over 2. ek pi over 2, yeah. So if you cross multiply, so this one will times this, so at the end of the day you get E0 is equal to B into minus k pi plus 1. Okay, no, there is a minus at the back here. There is a minus here, there is a minus here, so you put minus here, so there is also a minus here. So now at this point, you know, in maths, when two numbers multiply themselves to give you 0, so it's either A is 0 or B is 0, or both of them are 0. So at this point, for this to be 0, it's either B is 0 or this is 0. Do you get? So, but then let's see whether one of them can be 0. Let's see. For this first one, we have E minus k pi over k pi plus 1. So this one is E0, that is the question. So let's see. This can also be written as this. You know that for this to be 0, this E minus k pi has to be 1. Right? So for this thing to be equals to 0, this one has to be 1. But this function can be 1. Can be 1. This can be 1. Since what? 0. Yes, our k is not 0. Because remember, we defined our lambda. Our k is not 0 here. So the only way this can be 0 is if k is 0. Exponential raised power of 0 will give you 1. But k is not 0. Remember, we define our lambda to be less than 0. And then we define our lambda to be equals to minus k squared. So if k is 0, then this condition of less than 0 can never be satisfied. So k is already greater than 0. And if k is 0, meaning we are having lambda equals to 0, and that is case 1, we get. So for this case, our k is not 0. K is not 0. So that is why I say, since k is not 0, this can be 1. And if this expression can be 1, then you can't get 0. So it means that 1 minus exponential minus k pi, this can give me 0. So the only thing that can give us 0 here is if the b is 0. So therefore b is equal to what? 0. So with a being 0 and b equals 0, it means that your y, because our y is a exponential, is it kx plus b exponential minus, this is our a. So with a being 0 and b equals 0, it means that your y is 0, which is also a what? A trivial, this is a trivial solution. It's a trivial solution. So this case also gives us a trivial solution. So let's move on to case 3. So lambda, do you know the first case we did lambda equals 0, the second case we did lambda less than 0. Now let's do lambda greater than 0. At this point you can say let lambda be equals to k squared. Let lambda be equals to k squared. So our differential equation d2y dx squared plus lambda y equals 0 will be d2y dx squared plus k squared y equals 0. So getting the auxiliary solution, we get m squared plus k squared equals 0. M squared is equals to minus k squared. So you take the square root of minus k squared. So this will give you complex solution, which is plus and minus ki. So with this solution, we have a complex solution, and you know from the previous lectures, y is, if you have a complex solution, this will be your general solution. We get exponential alpha x into a cos beta x plus c plus b sine beta x. So remember your complex solution is like this: alpha plus minus beta I. So your alpha is the real part, while the beta is the coefficient of the complex part. So if you look at this solution that we get, our alpha is 0, then the quotient of the complex part is k, so beta is equal to k. So now you put raised power of 0, then you write a cos beta is k, then b sine kx. Anything raised power of 0 is 1, so you have a cos kx plus b sine kx. So this is the general solution. So now you also use the boundary condition so that you can get your unique solution that is required. So you say at s equals 0, y is equal to 0. So you say 0 is equal to a cos 0 plus b sine 0. So by now you should know cos 0 is 1. If you use your calculator, y sine 0 is 0. So it means that a is equal to 0. That is what it means, because this one will be a, this will be 0. So a is equal to 0. So let's get the other one. So let's use the other boundary condition. At s equals pi over 2, y is equal to 0. So now you put 0 for y, then your a is already 0, then you get k, then pi over 2 plus b sine k, then pi over 2. Okay, so with this, because what is multiplying cos is 0, what is multiplying cos is 0, so the whole of this is 0. Then so we get b sine k pi over 2. So this is just b sine k pi over 2. So just like case 2, when you get to this point, we have to discuss which of them is 0. So if we assume that b is not 0, it means that it is sine k pi over 2 that will be 0. So let's see if this guy is 0. You know, in sine, there are some values, there are some angles that sine function is usually 0. What are those values? If you use your calculator, you press sine, apart from 0, sine 90, sine 180. Sine 180 will give you 0. You press sine 260. You know, pi is equal to 180. So sine pi is just telling you sine 180, which is 0. Sine 2 pi is 360, which is still 0. Sine 3 pi is still 0. So it means that this k pi over 2 will be equals to n pi. And why are we saying n pi? Why are we not just saying pi? It's because it is not only sine 90 degree that gives us sine 180, sorry, that gives us 0. Sine 360 still gives 0. Sine 540 gives 0, and anything that you use to, as long as you use a number to times n to times pi, like any number times this pi, you will always get 0 for sine. So that is, you have to consider all those values, not just one. So that is why we have n pi. So in this n pi now, the 180 is there. That is when n is 1. When n is 2, it's there. When n is 3, it's there. Like that. So at this point, you can cross multiply 2 times, get 2n pi. So if you divide both sides by pi, you get k 2n pi over pi. So that is 2n. So this is our k. So remember that we said lambda is equals to k squared. So which means lambda is equals to this guy squared, 2n squared, which is 4n squared. So let's go to our final solution. So, but you know, this lambda depend on n now. The value of lambda actually depend on what n is. So we can actually say it is lambda n, and n is moving from 1, 2, all the way to infinity. So next thing is coming back to this formula, the general solution that we got earlier, a cos kx plus b sine what, kx. So we have what is it called, we have the value of a to be 0 and the b wasn't 0 and then we've also gotten the value of k to be 2n. So remember this problem we are solving, the question asks us to get, let me go up a bit. The question says we should find the eigenvalues and the corresponding eigenfunctions. So I haven't gotten that as the question. So this is the eigenvalues. This lambda now, these are the eigenvalues. So we want to get the corresponding eigenvectors. Okay, so now a is 0, so that part is gone. So we have your b, then you have your sign, your k is 2n, yes, and then we have our x. So because the eigenfunction depend on n, so it has to be yn, then your b2 also has to be bn, then you have this. So you see your n run from 1, 2, 3 all the way to infinity. It's 3 dots, so don't put 10 dots in your work. So when y is 1, so you get b1 sine 2nx. When y is 2, you get b2 sine 2nx, like that. So this is the eigenfunction, and these are the this is the eigenvalue, this is the eigenvector. Thank you very much. So see you in the next video. Before you leave, make sure you subscribe. See you in the next video.